There is a machine floating in the darkness of space, 1.5 million kilometers from Earth, colder than almost anything in the known universe, pointed at the edge of time itself. And what it is seeing, what it has been quietly transmitting back to us, is not confirming what we know. It is dismantling it, not slowly, not gently. With every image, with every spectrum, with every data packet that arrives on our screens, the James Webb Space Telescope is doing something no one publicly prepared you for. It is proving that the universe we thought we understood does not exist. Something is wrong with physics, not slightly wrong. Not wrong in the way that scientists enjoy arguing about at conferences and then resolve over the course of a decade. Wrong in the way that stops a room full of Nobel laureates cold. Wrong in the way that makes a cosmologist stare at a screen for minutes without speaking. And the machine responsible for exposing this wrongness is not a weapon, not a government program, not a conspiracy. It is a telescope. A telescope that was supposed to give us answers and has instead handed us a crisis so deep, so structural, so fundamental, that the entire framework through which humanity has understood the cosmos is now shaking. Let's start with what James Webb actually is, because most people still don't fully appreciate the magnitude of what was launched on Christmas Day 2021. Webb does not orbit the Earth. It sits at a gravitational sweet spot called the second Lagrange point, a location where the combined pull of the Earth and Sun holds it perfectly in place, 1.5 million kilometers out. Its primary mirror, a gold-coated hexagonal mosaic stretching 6.5 meters across, is nearly 3 times larger than Hubble's. Its instruments operate at temperatures approaching minus 233 degrees Celsius, colder than deep space itself, making it sensitive enough to detect the heat signature of a single bumblebee on the surface of the moon. And it doesn't see light the way your eyes do. It sees infrared, the invisible, the ancient, the light that has been stretched and redshifted across billions of years of cosmic expansion, carrying information from an era so distant that the universe itself was barely recognizable. When you can see things that far back, you expect to find a simple universe, young, raw, primitive. That is what the models predicted. That is what decades of theoretical physics told us we would find. What Webb actually found is something else entirely. The first images arrived in July of 2022. Scientists had been waiting for them for years. Engineers had spent decades designing this machine. And when those initial deep field exposures came back, when astronomers began processing the data, the reaction inside scientific institutions was not celebration. It was confusion. Because the galaxies Webb was seeing in the earliest moments of the universe were not small. They were not primitive. They were not simple. They were massive, bright, complex, chemically enriched. They looked like galaxies that had taken billions of years to build, except they existed just a few 100 million years after the Big Bang, in a window of time when they had no business looking like that at all. Think about what that means. Imagine discovering a fully constructed skyscraper buried beneath a layer of rock that geologists tell you is 50 million years old, before cities existed, before humans existed. That is the kind of impossible you're looking at when you examine Webb's early universe observations. These were not slightly ahead of schedule. They were structurally, mathematically, impossibly premature. And the scientific community's initial response was exactly what you might expect from people who have spent entire careers building models that now appear to be wrong. Some said it must be a calibration issue. Some said the redshift measurements needed more verification. Some said there were systematic errors in the data. But here's the thing about Webb. It was built specifically to eliminate those excuses. Its instruments are the most precisely calibrated in history. Its measurements have been cross-checked, peer-reviewed, and verified by independent teams across multiple countries. By 2025, the data was no longer ambiguous. A growing list of unexpectedly luminous young galaxies had been confirmed as real, challenging existing theories about how quickly stars and galaxies could form after the universe began. And as one MIT researcher put it when describing what they were seeing, we were able to see farther than humans ever have before, and it looks nothing like what we predicted. Nothing like what we predicted. Sit with that for a moment. Astronomers at the University of Missouri, using Webb, uncovered 300 unusually bright cosmic objects that may be some of the earliest galaxies ever formed. Objects so luminous, so unexpectedly developed, that they have no clean explanation within our current understanding of cosmological evolution. 300 of them. Not one anomaly, not a handful of outliers that could be dismissed as statistical noise. 300 objects that the standard model of the universe simply cannot produce on the timeline we observe them. And what most people are not seeing in the coverage of this discovery is that 300 is not a ceiling. It is a sample. It is what Webb found in a narrow slice of sky in a limited survey over a limited observation window. Extrapolate that across the full observable universe, and you are looking at a problem of almost incomprehensible scale. But the early galaxy crisis, as destabilizing as it is only one thread in a much larger unraveling. Because there is a second problem, and this one goes even deeper. It is called the Hubble tension. And if the early galaxy findings are the crack in the wall, the Hubble tension is the crack running through the foundation itself. Here is the core of it. The universe is expanding. That has been known since Edwin Hubble observed it in the 1920s. The rate of that expansion is described by a number called the Hubble constant. For decades, physicists have been trying to nail down the precise value of that number because it determines everything: the age of the universe, its ultimate fate, the behavior of dark energy, the architecture of space-time. And for decades, there were two main ways to measure it. You could look at the early universe, specifically at a phenomenon called the cosmic microwave background, the faint radiation left over from the Big Bang, and calculate what the expansion rate should be based on known physics. Or you could look at the local, present-day universe using distance markers like exploding stars called type Ia supernovae and measure the expansion rate directly. These two methods should give the same answer. They do not. While the standard model yields a Hubble constant of about 67 to 68 kilometers per second per megaparsec, measurements based on telescope observations of the present universe regularly give a higher value ranging from 70 to 76, with a mean of 73 kilometers per second per megaparsec. That might sound like a small difference, 5 or 6 units, but in physics, that gap is a chasm. This mismatch has perplexed cosmologists for more than a decade, because a 5 or 6 kilometers MPC difference is too large to be explained simply by flaws in measurement or observational technique. When numbers that are supposed to match don't match, when two completely independent measurement systems using completely different physical phenomena consistently arrive at different values, the universe is telling you something. And what it is telling you is that one of your assumptions is wrong. The most hopeful explanation was always human error, bad data, contaminated measurements, faulty calibration of the telescopes we were using. And that is precisely why James Webb was so eagerly awaited by the cosmology community. If Hubble's measurements were being distorted by crowded star fields, by dust interference, by the limitations of aging optical technology, Webb would see through all of that. Webb would clarify. Webb would resolve the tension. That was the plan. Webb did not resolve the tension. The James Webb Space Telescope confirmed that previous Cepheid measurements were accurate. The stars used as distance markers by the Hubble Space Telescope were measured again by Webb with its superior resolution, and the results matched. The problem was not the telescope. The problem was not the method. The problem was not the data. Nobel Prize-winning physicist Adam Rees stated, "We've now spanned the whole range of what Hubble observed, and we can rule out a measurement error as the cause of the Hubble tension with very high confidence." And then he said something that every person watching the news cycle in 2025 should have heard, but most did not. "What remains is the real and exciting possibility we have misunderstood the universe. We have misunderstood the universe." That is a Nobel Prize winner. Not a fringe theorist, not a science blogger, not someone with an agenda, standing before the scientific community and saying that the governing model of reality, the framework that has guided physics for nearly a century, may be fundamentally incomplete. And the machine that proved it is Webb. As of late 2025, the Hubble tension remains the most significant puzzle in cosmology, with the persistence of this disagreement suggesting that the standard model of the universe may be incomplete. Now here is where it gets stranger. Because James Webb has not just confirmed old problems, it has opened new ones. Consider what Webb revealed about dark matter, the invisible substance that makes up roughly 27% of the universe's total mass energy content. The substance that holds galaxies together, that forms the structural skeleton of the cosmic web, that physics tells us should exist everywhere, but that no experiment has ever directly detected. For decades, the dominant theoretical model for dark matter was something called cold dark matter, a particle-based framework in which dark matter moves slowly in clumps into dense halos around galaxies in a very specific, mathematically well-defined way. The predictions of this model have guided cosmological simulations for 30 years. Webb revealed unparalleled details about the early universe, including observations of young galaxies with unexpectedly elongated shapes that challenge established cosmological models. These are not the compact spherical clumped structures that cold dark matter predicts. They are filamentary, stretched, connected in smooth thread-like networks that look nothing like the simulations physicists have been running. And what the researchers found when they compared these observations to different theoretical models is deeply unsettling. The elongated structures are more consistent with what would be expected from warm dark matter or wave dark matter, scenarios in which dark matter behaves not as a cold, clumping particle, but as an ultralight quantum field that maintains smooth, wave-like structures across enormous scales. In other words, the most fundamental invisible ingredient of the cosmos, the thing that we have never directly touched, never directly measured, but whose existence we have inferred from its gravitational effects, may not be what we thought it was at all. And this is not a marginal result published in an obscure journal. The research was published in Nature Astronomy and included experts from MIT, Harvard, and leading institutions in Taiwan and Spain. These are not outsiders. These are the people who built the models, who wrote the textbooks, who trained the next generation of physicists, and they are looking at Webb's data and saying, the model doesn't match what we see. Let's go further, because Webb's revelations do not stop at dark matter. Researchers using Webb identified an ongoing merger event of at least 5 galaxies, occurring approximately 800 million years after the Big Bang, along with evidence that the collision was already redistributing heavy elements, oxygen, and other products of stellar fusion, far beyond the boundaries of the galaxies themselves. Before Webb, the scientific consensus held that complex multi-galaxy mergers and widespread chemical enrichment of this kind should not have been common until well over a billion years after the Big Bang. This discovery shows those processes were already underway far earlier than models predicted. As one of the researchers explained, this tells us that theories of how galaxies assemble and how quickly they do so need to be updated to match reality. Not refined, not tweaked, updated to match a reality that they currently do not account for. Read that again. The theories need to be updated to match reality, not the other way around. This is the thing that mainstream coverage keeps missing. Every one of these discoveries is being reported as an exciting find, a remarkable observation, a fascinating puzzle. And that framing is not wrong exactly, but it is dangerously incomplete. Because what is actually happening is that Webb is conducting a systematic audit of modern physics, and the audit is returning failures across multiple departments simultaneously. Galaxies shouldn't be that massive that early. The universe shouldn't be expanding that fast. Dark matter shouldn't be distributed in that pattern. Galaxies shouldn't be colliding and enriching themselves with heavy elements that quickly. These are not isolated anomalies. They are a pattern. And the pattern points in one direction. The standard model of cosmology, the lambda-cold dark matter model, the framework that has unified our understanding of the universe for decades, is missing something significant, something that changes the picture entirely. As one researcher summarized it, cosmology as we know it may be broken. If the Hubble tension isn't a mistake in the measurements, we will have to come up with new physics. New physics. Those two words, in the mouth of a working cosmologist, carry a weight that cannot be overstated. New physics means new particles, new forces, new behavior of space and time itself. New physics means that the universe operates according to rules we have not yet discovered. And what Webb is telling us, with increasing clarity and increasing urgency, is that new physics is not a theoretical fantasy. It is a measurement result. Consider the specific problem of what researchers are calling little red dots. In August 2025, astronomers may have uncovered the origins of some of the strangest galaxies in the early universe, tiny but brilliant objects discovered by Webb that had resisted explanation for years. Some researchers propose that these were not conventional galaxies at all, but rather a completely new class of cosmic object. Structures involving the merger of supermassive black holes and stellar matter in configurations that have no precedent in existing theoretical frameworks. This is not science that builds on what we know. This is science that has run out of known territory and is now mapping the edge. And then there is the interstellar visitor. In late 2025, astronomers turned Webb toward interstellar comet 3I Atlas as it moved away from the Sun, using its near-infrared spectrograph to map the chemical composition of this object. What they found was striking. The composition of 3I Atlas was significantly different from comets originating in our solar system. An object traveling between stars, carrying the chemical signature of another stellar system entirely, and Webb was able to read that signature the way a forensic analyst reads DNA. That capability, that level of precision, means that every assumption we make based on the composition of our own solar system's material now has to be questioned. If objects from other stars carry fundamentally different chemical fingerprints, what does that tell us about the diversity of planetary systems, the distribution of elements, the conditions under which life might or might not emerge elsewhere in the galaxy? But perhaps the discovery that is most quietly unsettling, the one that receives the least coverage despite its profound implications, is what Webb found inside a dust-shrouded galaxy called IRS 07251 or 0248. Deep inside this heavily concealed galactic nucleus, researchers detected an extraordinary concentration of complex organic molecules, including benzene, methane, and even the highly reactive methyl radical, never before detected outside the Milky Way. These are the molecular precursors to amino acids, the building blocks of the building blocks of life. And Webb found them not in our galaxy, not in a nearby star-forming region, but in the core of a distant, dust-enshrouded galaxy that traditional telescopes could not even see inside. The evidence points to cosmic rays as a key factor in driving the chemical richness observed, which means that the mechanism for generating life's precursors may be far more widespread, far more energetically driven, and far more ancient than biology has previously assumed. Think about what that means for the question of life in the universe. If complex organic chemistry is not a rare accident confined to favorable star systems, but instead a process actively driven by cosmic radiation in the cores of galaxies billions of light years away, then the raw material for life is not scarce. It is everywhere. It is built into the deep architecture of the cosmos. And that is not a comforting thought. That is a question with consequences so large that most institutions are not yet prepared to address them publicly. What Webb is constructing, discovery by discovery, is not just a new map of the universe, it is a demolition of the old one. And the timing matters, because we're not at the beginning of this process. We're not in the early days of Webb, when anomalies could be attributed to instrument calibration or processing errors. We are 4 years into operation, with petabytes of verified data, cross-checked by hundreds of independent research teams across 14 countries. Over 500 researchers have come together in the Cosmoverse Consortium to produce a comprehensive white paper delving into the various cosmological tensions between theory and observation. Not to dismiss these tensions, but to take them seriously enough to dedicate a global scientific collaboration to resolving them. That is the scale of the response that Webb's findings have provoked. And here's the part that nobody in popular science coverage is saying clearly enough. The resolution to what Webb has uncovered is not going to be a small adjustment. It is not going to be a footnote. Historically, when physics encounters anomalies of this magnitude, when measurements consistently and reproducibly contradict theoretical predictions across multiple independent methods, the resolution has always required a paradigm shift. Newtonian mechanics could not explain the precession of Mercury's orbit, and the resolution was Einstein's general relativity, a complete reimagining of gravity and spacetime, the ultraviolet catastrophe in thermodynamics, the failure of classical physics to explain the behavior of light emitted by hot objects, could not be patched. Its resolution was quantum mechanics, and with it, the entire probabilistic, non-deterministic architecture of the subatomic world. The anomalies Webb is uncovering are not smaller than those. They may be larger. As one physicist involved in Hubble tension research put it, this is the dream of every physicist. Find something wrong in our understanding so we can discover something new and profound. That statement sounds almost optimistic, and in a scientific sense, it should be. Because if Webb is right, and increasingly the data suggests it is, then what lies ahead is not the collapse of knowledge. It is the expansion of it. A new physics, a new cosmology, a new understanding of what dark matter is, of what dark energy does, of why the universe expands the way it does, of how structure formed so rapidly after the Big Bang, of how organic chemistry seeds itself across billions of light years of interstellar space. But here is what that transition means in practice. Every calculation that rests on the current standard model, every cosmological simulation, every dark matter detection experiment, every theoretical framework that attempts to predict the large-scale structure of the universe is potentially operating on flawed assumptions. The numbers are still useful, the observations are still valid, but the interpretation of those numbers, the story they are being made to tell, may be incomplete in ways that we cannot yet fully articulate because we don't yet know what we're missing. Webb is still operating, it is still transmitting. Every day, new data arrives at the Space Telescope Science Institute in Baltimore, processed by teams of scientists whose job it is to translate light into understanding. And every week, new preprints appear on research servers, new peer-reviewed papers emerge in journals like Nature Astronomy and the Astrophysical Journal, each one adding another data point to a picture that is becoming progressively harder to reconcile with what physics textbooks currently say. The machine is not slowing down. It has a designed operational lifespan that runs well into the 2030s, with sufficient fuel reserves that some estimates project it could remain functional for decades beyond that. Which means this is not a crisis with a fixed endpoint. This is not a puzzle that will be quietly resolved in a lab somewhere and then announced at a press conference. What Webb has started cannot be unstarted. The anomalies are documented. The tensions are measured. The data exists, and it is public, and it points in a direction that every honest physicist now has to acknowledge. The universe does not match the model. And the model has to change. The question is not whether physics will break. It already has. The question is what replaces it. Whether the answer lies in a new understanding of dark matter as a quantum field rather than a classical particle. Whether it requires the introduction of early dark energy, a brief phase of accelerated expansion just after the Big Bang that current models do not include. Whether it demands a revision of Einstein's equations at cosmological scales. Whether it opens space for entirely new particles, new forces, new symmetries that our current instruments are not even built to detect. Whether the universe has a structure so different from what we imagined that the resolution, when it comes, will feel less like a correction and more like a revelation. Nobody has that answer yet. And that is not a failure of science. That is science operating exactly as it is supposed to, pushed to its edge by an instrument powerful enough to see what was always there, waiting to be found. James Webb did not break physics. It only showed us where physics was already broken. What we do with that knowledge, how quickly we adapt, how honestly we confront the gap between what we believed and what is actually true, that is the story still being written, and the telescope is still watching.